Okay, so it's just another little dimensional analysis mole problem. We have an unsuspecting hiker that thinks he's found some Queen Anne's lace or wild carrot, which is edible, but he's actually harvested the very poisonous lookalike poison hemlock, which contains this molecule called conine, and it has a molar mass of about 127 grams per mole. It's toxic at 8 milligrams per kilogram, which means that if you weigh 52 kilograms, 416 milligrams is a potentially toxic dose, and it's present in levels up to 2% by weight in the plant. So the first question is, our unsuspecting hiker eats 200 grams of poison hemlock. It doesn't really matter what part of the plant he ate. Determine, has he made a fatal mistake in picking out a wild plant to eat, or will he live on the hike another day? First, we have to figure out, not this whole thing is this toxic molecule, conine, right? So we go to 200 grams eaten and 2% by weight, or 0.02, right? And another easy way to do this would be to remember that 1 gram is 1% of 100 grams, right? So either way you figure this out, you get 4 grams eaten. We need to convert that to milligrams. So 1 gram, 1,000 milligrams. Just warming up with a little quick dimensional analysis. Cross those out. We get 4,000 milligrams, but because toxicity depends on who you're giving it to, right? Like the amount of ethanol that would kill a mouse is a lot smaller than the amount that would kill a human. Weight matters, so we have to compare his dose per weight. 4,000 milligrams over 61 kgs. Comes out to about 65 milligrams per kg, which is much, much, much higher than the toxic dose of 8 milligrams per kg. So I'm just going to draw a little a toxic dose here. The next part of the question is, how many moles of conine has our hiker eaten? And the good news is we've already done a good part of this. We figured out that he ate 4 grams, right? And we just need to go from grams to moles. So 4 grams. And honestly, I could assume sig figs get a little funny here because I told you 2%, but that 2% is actually a measurement, right? And it has specificity up to this number of digits. So we could say 0.0 grams, and then 127.231. That's a lot of sig figs. Grams per 1 mole conine. And then cross out our units that cancel. And when I do this, what do I get? I get 4 divided by 127.231. I get 0.03 yada 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 moles, but for the sake of the number of digits we have in this measurement, which is probably the most difficult one to get a measurement of, if we're talking about analytical chemistry, we're going to go with 0.03 moles, and it was a toxic dose. Okay, so the next question is about isotopes. Selenium has a Z number of 34, is named after the moon, but it is not any more abundant on the moon than it is on Earth. It's actually really rare. you know, pretty much everywhere we would go. And there are a lot of nice isotopes of these. I say there are 9. There's way more than that, but a lot of those are synthetic and made for lab purposes. So there are 9 in general, and 6 of those are stable in ways that we are meaningful and we can measure them and they stick around. So given the following isotopes, we're asked to calculate the following. How many neutrons are in each, and what is the atomic mass of selenium given this data about the isotopes and their abundance. So the first one should be pretty easy as long as you remember what this number means. So sometimes students get mixed up when we write this out and they think that this is the atomic number. And it's not, though I get why why someone would think that, but it would be redundant because our Z number is told to us by our element symbol. So we can always take this symbol and then look up the Z number or the number of protons. This is here to, oops, I lost my mouse. This is here to tell us what isotope we're dealing with, right? And what the approximate atomic mass of this isotope is. So to figure out the number of neutrons, we just remember that neutrons equals atomic mass of your isotope minus Z, or you can remember that P protons plus neutrons equals total mass. And then you could remember that Z is protons because the number of protons is what's determining the identity of that element. So to do this, we just have to take 74 minus our Z number, 34, 74 minus 34, and so on. And we get 40 neutrons. And then when you have a bunch of them like this, you can either keep doing this math, right, to get 42, or you could start counting up. I think it's easier to not get lost if you keep doing the math, but you can always find ways to check yourself. So 78 minus 34 is 44. And then I'm adding 2 units, and I know they have to be neutrons because they can't be protons. Otherwise, I've changed elements entirely. So this must be 46. And then I've added another 2. So this must be 48. So we filled out all the neutrons. And the second part of this question asks, what is the atomic mass based on these isotopes? So what's the average atomic mass? We know what they are for each of these isotopes, right? It says, but what if we have an atom of selenium, or we have a reaction with a random sample of selenium, and we want to convert that to moles? So we need the average atomic mass. And this is a weighted average, right? So I would do this the same way. Say if you had 3 exams, right? And they were all worth 1/3 of your grade. You would say 0.33 plus 0.33 plus 0.33. This is for exams, right? And say on the first one, you got a 76. And then on the second one, you studied a lot harder and you got a 91. And then on the third one, you did somewhere in the middle. And you want to know what your grade is going to be before it's posted. So you calculate all this and add it together. So 0.33, I'm making these numbers up on the fly. So I am 25.08, 33. So I'm doing the math in real time. 30.03. Right, 26.4. And then you would add these all together and you would know that your grade was an 81. right? And because these are equal weights, you could do this by doing a standard average where you just divide by the number of things, but that's almost never going to be the case for elements. So you can treat it as always a weighted average like this, or just the long form of an average. This will get you the same place as dividing all these numbers by 3 would, but it explicitly tells you what each test was worth. So we can do that for our selenium. And I've written that out. Ooh. Right. So first isotope is not very abundant, 74, and we have to convert percent into decimal point to do this. So 0.0086 equals 0.6364. And then our next one is 76. Isotope 75 is unstable, so we skip over it because it does not exist long enough to be in any random sample you might find. So you shouldn't be needing to do chemistry with it, right? And then 77 is contributing 7%, right? Yeah. 0.0760 equals 5.852. And then we get to our second biggest contributor, 78 times 0.2369 is going to be 2.47. 80 is our largest contributor. Almost half of all selenium is the 80 isotope. And we get 39.84. And then 82.882, 7.23. So I'm missing what digit this was. So I'm just going to do it again because I didn't write it down the first time I did it. 2324. And then you add this all together, right? One place you can check yourself here is you're never going to have an isotope that makes up more than 100% of any of your, you're never going to have an isotope that is more than 100% abundant, right? So all of your numbers that come out on this side should be less than what you put in, right? That makes sense, they're fractions. And if we add these all together, what we get is 79.06, which is within 0.1 of the official atomic mass of selenium. The official one's a little bit higher, and this has to do with discrepancies of when it was measured, who measured it, and the details, like how much percentage of this, how precise this measurement actually is. Right? So we get pretty close. So selenium, if you don't know what isotope you have a big old chunk, your average atomic weight is going to be 79.06 approximately grams per mole. Okay, so our next question is about vitamins, and this is an empirical formula kind of question. So I have a sample that's labeled vitamin B6. It's always good to label your samples, but vitamin B6 actually refers to several compounds, more than these 3. Sometimes they're called vitamers, right? To distinguish that they aren't all the exact same chemical. So to determine which one you have, you conduct an elemental analysis and determine that your sample has the following percentages of carbon, hydrogen, nitrogen, and oxygen. So what always tricks me up when I have to do an empirical formula problem like this to figure out what vitamer I have is they don't tell you how much sample you have, but that's okay. What I always do is choose an easy amount of sample. It's already in percentages for you, so you can choose anything. You can say I have 1 kilogram of sample. You can say I have 2 micrograms of sample, right? I think it's easiest to choose an easy amount, right? Because it's going to make the math easier for you. So I always say I have 100 grams. And then if I have 100 grams of sample and 57.12% of it is carbon, I know that 57.12 grams of carbon are available to me, and so on and so forth. So what we have to do is convert all of these into moles. So 57.12 grams of carbon. Carbon is 12.01 grams. 1 mole equals 4.75. And then I'm going to start writing our unreduced, totally raw empirical formula that we get from here. So we can do hydrogen. So if I have 100 grams and 7% of those are hydrogen, I have 7.19 grams hydrogen. This is where it matters that you start writing down which element you're working through on your dimensional analysis, or else it can get really messy. 1.008 grams of hydrogen, 1 mole hydrogen equals 7.10. And then I'm going to clear us up some space for nitrogen. So if I have 100 grams of sample of an unknown and 16.66% of it is nitrogen, I know that I have 16.66 grams of nitrogen in my theoretical 100 gram sample mass. 14.01 grams of nitrogen to 1 mole. You're going to want to have a periodic table here with you for obvious reasons. That's 1.19. 1.19. Then we can do oxygen last. 19.03 grams, right? Because 19% of 100 grams. So this little guy didn't get crossed out. 19.0. Ooh. See, this is why I like the ladder. It keeps me from writing down silly stuff. 16.00 grams oxygen, 1 mole oxygen equals 1.19. And without even solving for the empirical formula, there's kind of a clue here, right? Because out of all of these, the nitrogen and oxygens are pretty clear. And the only one that has a 1-to-1 ratio of nitrogen and oxygen is this pyridoxyamine, this one in the middle. But I can divide all of these by the lowest number that I get. So if I divide everything by 1.19, it comes out to me as 3.99 carbon, 7 and 101. And that's really close. I'm going to round to 4 carbons to 6 hydrogens, 1 nitrogen, and 1 oxygen. And this is the empirical formula that matches this molecular structure. And to check, if you wanted, you could just times 2. Never, ever, ever do this otherwise. This is only for making sure your empirical formula lines up. This does not work in stoichiometry. This will not work for balancing equations, but we can see that this, if we bump up our empirical formula twice, we get the molecular formula. So we know that our unknown sample was this vitamer, and it can't have been any of these other 2. Okay. So our next question is about acid rain. So statues, buildings, monuments, all kinds of stuff. It's made out of marble. and it weathers because of exposure to the elements. And one of those causes is acid rain. Marble is mostly calcium carbonate right here. And acid rain we can represent simply as a solution of sulfuric acid. So if 50 liters of acid rain fall on the Taj Mahal to react with the marble, and the Taj Mahal weighs about 2.5 thousand trillion kilos. So let's assume for now that marble or calcium carbonate is our excess reagent because we have such a large mass of it that it's almost unmeasurable. If the concentration of the sulfuric acid is 0.5 millimolar, determine and using the equation below, determine the following. So how much marble is missing from the Taj Mahal as a result of this acid rain, and what mass of CO2 has been released as a result? The first thing we have to do is make sure our equation's balanced, right? So I'm going to just draw a line and start itemizing everybody. We have a lot of elements here. And then 1 calcium here, 1 carbon, 2 hydrogens, 1 sulfur, and then 3 plus 4 is 7 oxygens, and 1 calcium, 1 carbon, 2 hydrogens, 1 sulfur, and then 4 plus 2 is 6 plus 1 is 7. So this comes balanced as it is, which is handy because it means we can just move on. All right. So now what mass of marble is missing? This is a stoichiometry equation. It's a stoichiometry problem. So first we have to convert concentration to moles of our starting reactant that we have a good measurement of, and we know is going to be our limiting reagent because there is just so much marble in the Taj Mahal. So if we have 0.5 millimoles per, draw my big line for dimensional analysis per liter, right? Because this is millimolar. So if moles is moles per liter, millimolar is millimoles per liter. So we have 0.5 millimoles per liter, and we need to convert that into moles. So much like milligrams to grams, 1,000 millimoles, I'll write it out. Millimoles is 1 mole. And then we had 50 liters, and we can cross out things that cancel. Millimoles cancels, liters cancels. So we get 0.2, oops, missed a 0. We get 0.025 moles H2SO4 react. Okay, but that doesn't yet tell us how much marble has been degraded. So we're going to use this number for our next part. And now we have to figure out how we relate this back to our marble degraded. So 0.025 mole H2SO4. And then we look at our stoichiometry. There is an implied 1 here, an implied 1 here. So that is my molar ratio, right? So 1 mole H2SO4 will react with 1 mole calcium carbonate. And then we have to figure out 1 mole calcium carbonate has a molecular weight of what? So molecular weight of calcium carbonate. I've done it ahead for myself, but if you go to your periodic table and look up your atomic weights, you can figure out your molecular weight. It is 100.09 grams per mole. So I put that on top. 9 grams calcium carbonate. And then moles sulfuric acid cross out, moles calcium carbonate cross out, and we're left with grams calcium carbonate. And this comes out to 2.5 grams calcium carbonate deteriorated. And then I'm going to just write this down on top so we can have space to look at the second question. So the second question asks something similar. What mass of CO2 has been released into the environment? What mass of CO2 has been released into the atmosphere as a result? In this, again, we have our implied 1, so it's a stoichiometry problem. And we know that we started with this many moles. We could actually go back and convert this from 2.5 grams calcium carbonate, right? We could switch this around. We could ask, based on the deterioration of this much calcium carbonate, how much CO2 was released. But we already have this sitting nicely for us in moles. So that's where I'm going to start. 0.25 moles H2SO4. And then 1, 2, 1, right? Because this was already balanced, so we have an implied 1. 1 mole H2SO4, 1 mole CO2, and then we have to figure out 1 mole CO2, and you need to figure out the molecular weight for CO2. This one I remember 21 pretty well, right? So carbon is 12 plus 1 oxygen plus another oxygen. These together are 32 plus 12 equals 44, right? So 44 grams for 1 mole CO2. Cross out, cross out, cross out, cross out. Oh, here I've done a classic mistake. See, I should have written CO2 on top. And if we do our math across our dimensional analysis ladder, we get, or I get 1.1 grams of CO2 released in this acid rain marble deteriorating event. Okay. So this next question is a limiting reagent question. So we're going to need to figure out which of these is the limiting reagent and do a little stoichiometry and bounce some equations and name some elements. So it's good, it's comprehensive. So cyanogen is in the atmosphere of Titan, Saturn's largest moon, and just out here in space and interstellar nebulas, and it has some uses on Earth. And we are given the reaction in words, right? It says, in its reaction with fluorine gas, carbon tetrafluoride and nitrogen trifluoride gases are produced. So we know we're working with cyanogen plus fluorine gas. And here we have to remember our diatomic elements. So I remember this as Hunkelbrief, but you might remember it as Brinkelhoff. Okay, I learned Hunkelbrief. Brinkelhoff is new to me, but whichever one floats your boat. Either way, we know that this is a diatomic gas. So F2. And then we just have to remember our prefixes, carbon tetrafluoride and nitrogen trifluoride. So carbon tetra is 4, nitrogen trifluoride is 3. And I can see already that this isn't balanced, right? Like we have 2 fluorines here and then 7 over here, right? It's a mess. So I'm going to itemize this: carbon, then nitrogen, then fluorine, carbon, nitrogen, fluorine, and start counting. 1 carbon, 2 nitrogens, 2 fluorines, and 1 carbon, 1 nitrogen, 7 fluorines. So carbon's already balanced, so I'm going to do my best to not mess that up. So instead, I'm going to go fix my nitrogens. So I'm going to add a 2 here, cross this out 2, and then I get 2 times 3 is 6 plus 4, 10. And then this is going to work out nicely for me. So I add a 5 here because my carbons are good, my nitrogens are good. My fluorine is the only one messing me up. And that gives me 10. So I know that this is my fully balanced equation. So we can get rid of all the mess we got to get there. And let's see if I can just, ooh, yeah, I kind of can shrink it down. So there's our balanced equation. Then it says what mass of carbon tetrafluoride is formed when each reactant is mixed together, and we have 60 grams of each. So we have to figure out who is the limiting reactant. So fluorine, to do this, we need our molecular mass. Fluorine is elemental but diatomic, so you have to be careful when you look at this on the periodic table, right? Because when you look at fluorine on the periodic table, it's going to tell you for 1 atom, it's 19 grams per mole, but we are in a diatomic gas in our elemental state, so it's going to be 38. And then cyanogen is 12 plus 14 plus 14, and that comes out to about 40 grams per mole. So then we're going to set up our little effective moles trick. CN2, I'm going to make a little chart. F2, moles, and then effective moles. So to get how many moles of fluorine gas we had 60 grams, F2, and we looked up our molecular weight over here. It was 38.00 grams to 1 mole. F2, so 60 divided by 38, I get 1.58. And then I have another 60 grams of cyanogen, CN2. I do the same system. This one has a molecular weight of 40.03 grams per 1 mole. CN2, cross out grams. 60 divided by 40.03, it's going to be really close. It's going to be 1. I'm going to round it to 1.50. Okay. Then we have our effective moles. So that is going to be our number of actual moles, right, divided by our stoichiometric ratio. So there's a 5 there and a 1 there. So effective moles for cyanogen is 1.5, and then 1.58 divided by 5 is 0.361. So this is way less, right? So we know we're going to run out of fluorine first. You could also go through the trouble of determining how much mass you would get from 60 grams of each of these, and then seeing which one is less. That would also tell you which one's your limiting reagent. But we can see that we're going to run out of fluorine much, much more quickly than we will anything else. So we can move on doing our stoichiometry with fluorine. and set up our ladder. So 60 grams of F2 to convert that to moles, 38 grams, 1 mole, F2, and 5 moles, F2, remember, because that's our ratio, converts to, what are we looking for? We're looking for carbon tetrafluoride. So we want to know how much of this we make. Converts to 1 mole. Ooh. 1 mole CF4, and then we have one final problem figuring out what our molecular weight is. 1 mole CF4, and then the molecular weight of CF4 I don't have on hand, but that's okay, we can fix it. 12.01 for carbon plus 4 times 19 for the contribution of our 4 fluorines. So 12 plus 4 times 19 is going to come out to 88.01 because of our 01 from carbon grams. So 88.01 grams CF4. And then we can cancel this out, cancel that out, cancel that out. We're left with grams CF4, and that's what we wanted to find anyway. And we do all this math. So I like to do everything on the top and then everything on the bottom. So 60 times 1 times 1 times 88.01 divided by, open parentheses, 38 times 5 times 1. And I close parentheses, right? And I get 27.80 grams carbon tetrafluoride.